Hello, hello, and welcome to this video on polynomials and theory of equations. So the PDF which I will use, this is the PDF. The PDF which I will be using. You can download it from astavakra.org, which is my website, and you have variable in Algebra here. You can click this link, and you can download the PDF here. So 9 chapters are done with all the solutions. I have removed inequalities from this because I will probably write an entire separate book on inequalities. Right now I'm working on the last chapter, which is miscellaneous problems. So once that is done, it will be here. So you can see there are 9 chapters which covers the syllabus of 11th and 12th, and you have solution of all the problems given in these chapters. So you don't need to wait for my videos. If you want to study a different topic other than in videos, you can download and study from here. So with that aside, we can start the video of today. So let me set this in full screen mode, and this one also. Okay. We don't need this search bar. All right. So we have studied till problem number 80. We will try to do 10 more problems. That is problem 81 to 90. So as always, I will say that when I am reading the problem, you should pause the video and try to solve the problem yourself. And if you cannot solve the problem, then look at the solution. So without further ado, let's get started. Question 81 says that let P be a prime number. So that phi P of x is equal to x to the power P minus 1 plus x to the power P minus 2 and so on up to x plus 1 is irreducible. Now, in general, there are two kinds of problems. One of the problems which are based on straight up formula and you can just go and solve it. Or there are certain techniques to solve the problem. The second type of problems are those type of problems where you need to add something from your side. Now this kind of problem where you need to add something from your side is a difficult problem or is a hard problem. So this is a hard problem because we need to do something from our side. The reason is the given function phi p of x, which is given, we cannot apply Eisenstein's irreducibility criteria just like that, because there is no prime number, suitable prime number for all the coefficients as 1. So if you look at the solution, what the solution holds is, we represent this as x to the power p minus 1 by x minus 1. And then we substitute x plus 1 for x. And then it becomes x plus 1 whole to the power p minus 1 divided by x plus 1 minus 1, which gives us finally x to the power p minus 1 plus combination of 1 out of p, x to the power p minus 1 and so on. Now if you look at this equation, phi p of x plus 1, the coefficient of the second term up to penultimate term are all divisible by p, but the last term is not divisible by p square. So as you can see here, so the last coefficient is p, which is not divisible by p square, and therefore from Eisenstein's criteria phi p of x plus 1 is irreducible. Now if phi p of x is equal to gx plus hx, then phi p of x plus 1 is equal to gx plus 1 hx plus 1, which will give a factorization of phi p of x plus 1. Now we have proven that it is irreducible, so the factorization is not possible, and therefore phi p of x is irreducible. Now we look at question number 82. Question number 82 says that let f of x is equal to x to the power n plus 5 x to the power n minus 1 plus 3, where n is greater than 1 is an integer. Prove that f of x cannot be expressed as a product of two polynomials, each of which has its coefficient integers and degree at least 1. Now we rewrite the given polynomial as x to the power n plus 5x to the power n minus 1 plus 0 into x to the power n minus 2 plus 0 into x to the power n minus 3 and so on up to 0 dot x plus 3. Now if you take prime number 3, then you will see that 3 divides all the zeros, okay, and 3 square does not divide a0, which is 3, and it also does not divide an minus 1. Okay, so by extended Eisenstein's criteria, f has an irreducible factor of degree at least n minus 1. So if possible, let us take one factor of degree n minus 1, then other must be linear and monic as f is monic. This implies that f has integral roots. By integer root theorem, this root must be an integer divisor of 3. Hence, it would have to be 1, minus 1, 3 or minus 3. However, none of these roots of the given, none of these out of these 4 are roots of the given equation, and hence f is irreducible. Question 83 says that prove that for any prime p, polynomial x to the power n minus p is irreducible over set of complex numbers. Now we treat the given polynomial as an x to the power n plus n minus 1 x to the power n minus 1 and so on, where n is equal to 0. There is a typing mistake. N is 1 because x to the power n is 1. So this should be ai is 0, where I is from 1 to n minus 1, and a0 is equal to minus p. Now if you consider the prime given in the polynomial, then p divides ai, p does not divide 1, and p square does not divide minus p, and hence f of x is irreducible over z. You can see this in this example clearly. The coefficient of x to the power n minus 1 up to x is all 0, so p will divide them, but p square does not divide p. So now we move on to question 84. Prove that x to the power 7 plus 48x minus 24 is irreducible over z. So for 84 we consider for prime p. Now p divides ai for 0 less than or equal to n minus 1. There is a typing mistake, 0 up to n minus 1. So if you see 3 will divide 48, and 3 square does not divide 24. Okay, and p is not 1. So the polynomial is irreducible over z. Question 85 says that prove that x power 4 plus 2x square plus 2x plus 2 is not a product of two polynomials, x square plus x plus b and x square plus cx plus d, where a, b, c, d are integers. So this is a simple case. We take prime p, and then we can see that this 2 is divisible by 2, this 2 is divisible by 2, but this 2 is not divisible by 2 square, and therefore the polynomial is irreducible, and therefore it cannot be represented as product of two given polynomials. Now question 86 says that prove that x to the power 5 minus 36 x to the power 4 plus 6 x cubed plus 30x square plus 24 is irreducible over z. Now clearly you can see that all the coefficients are product of 3 or even 6, but 6 is not the prime number, so we will choose 3. So in this case we divide 3, all these 3 are divisible by 3, but this is not divisible by 3 square, so the polynomial is irreducible. So that's what this has given. Now question 87 says that prove that x power 3 plus 3x square plus 3x plus 5 is irreducible over z. Now this is a tricky one because there is no suitable prime for the given polynomial. So we substitute x is equal to x minus 3, we get x cube minus 6x squared plus 14x minus 10 is equal to 0, on which we can apply Eisenstein's criteria for p is equal to 2. So for p is equal to 2, this is irreducible. Now writing fx for original polynomial, we deduce that f of x minus 3 is irreducible, but a factorization of fx would give a factorization of fx minus 3. Hence fx is irreducible over z. Question 88 says that prove that x to the power p plus px plus p minus 1 is reducible for some prime p, then it must be 2. So now in this problem we see that the prime p will divide the coefficient of x, but it won't divide p minus 1 for p greater than 2. So if you see, this is the constant term. Now if p is a prime number which is greater than 2, then it won't divide it, because it will become, if the prime is p, then this will become p minus 1, and p minus 1 is not divisible by p square. So the prime will become unsuitable. But if p is equal to 2, then what happens is this polynomial becomes x square plus 2x plus 1, which is x plus 1 whole square. So if the polynomial has to be reducible, then the prime must be 2. Question number 89 says that let an x to the power n plus n minus 1 x to the power n minus 1 plus so on up to a1x plus a0 is a polynomial over z and irreducible over it. Prove that a0 x to the power n plus a1x to the power n minus 1 and so on is also irreducible over z, and use this to show that 21x to the power 5 minus 49x cubed plus 14x square minus 4 is irreducible over z. This term should be an, not a0. Now, so what we do is, we have been given that this polynomial is irreducible over z. So we substitute x is equal to 1 by x and we find that it is irreducible over z. Now we substitute x is equal to 1 power x in 21x to the power 5 minus 49x cubed plus 14x square minus 4, then it becomes 4x to the power 5 minus 14x cubed plus 49x square minus 21. Now if you see this, then these two terms, these three are all divisible by 7, which is a prime. And we see that the last term 21 is not divisible by 7 square. So the polynomial is irreducible over z. Now we come to the last problem. Problem 90 says that if a1, a2 up to an are elements of z and are distinct, then prove that x minus a1, x minus a2 and up to x minus n minus 1 is irreducible over z. So the solution is, we take two monic polynomials px and qx such that px into qx is equal to x minus a1 into x minus a2 up to x minus n minus 1. So we substitute that. If we substitute any of these ai as the root, then p of ai and q of ai would be minus 1. So now we see that p of ai and q of ai are integers. So we have two possibilities. One of the possibilities is that p of ai is equal to 1, q of ai is equal to minus 1. And the second possibility is p of ai is equal to minus 1 and p of ai is equal to 1. And in both the cases, the sum would be 0. But that is not possible because the sum cannot be equal to 0, which is the sum of monic polynomials, which have degree of less than 1. So from the fundamental theorem of algebra, it cannot have n different roots, and therefore there do not exist any such polynomials, making the given polynomial irreducible. So with this, we come to the end of our 10 problems on various equations. Now, I hope that you have found this video useful and it is helpful for your studies. And if you have questions or comments, make use of the comment box. If you want videos on any particular topic, make sure to use the comment box. And please do subscribe to the channel and share it, because if you find this worth subscribing and worth liking, then it should reach more people, and the YouTube algorithm will work in that way. So thanks a lot for watching. Enjoy.